In this example, I will simulate a simple buck converter using the values that I have written here in the comments, and I will try to verify the ripple components that I have calculated here. So first I'll place the components. I can place a voltage source using V. To place a MOSFET, I will go to the component library and I'll choose an NMOS, that is an N-channel MOSFET. Before I can place this, I can rotate it using Control R. I can also mirror it if I want to. I can place an inductor using L, a capacitor using C, a resistor using R, and a diode using D. So I can connect them using a wire. Then I need a ground terminal so that the voltages are referenced with this ground. I can also have a label for the switch node. I can move any component using this move option, and I can undo using F9. I can drag any part of the converters using this option, and I can delete it using cut and copy paste it using this option. Now I'll put the values that I've shown in the comments. For 72 volt for the input, 170 micro for the inductor, 100 micro for the capacitance, and 10 ohms for the resistor. Now before I run this schematic, I have to choose the MOSFET and the diode. If I right click on the MOSFET, I can pick new MOSFET. So these are a list of actual MOSFETs. These are real MOSFETs that you can buy and use in your circuit. So it is one of the specialities of SPICE that manufacturers can share the models of their devices and users can import them in their circuits and simulate them to see how they will work in the real circuit. So I'll choose a 200 volt MOSFET. As you can see, this MOSFET is not an ideal switch. It has an on resistance that is given in the data sheet of this device, so it will actually have some non-idealities. Similarly, I can choose a diode. Again, I can choose a 200 volt diode. So you can choose any device as long as you make sure that the device ratings are satisfying the values of your simulation. So my simulation has the maximum voltage of 72 volts, so 200 volt devices are satisfactory. Now I need to supply the gate voltage to the MOSFET. Practical gate drivers can be quite complicated, but to simplify it, I can use a simple voltage source. I have to connect this gate source with the gate and source terminal of the MOSFET. So I'll use the labels that I have created, and I'll create another label of gate so that I can connect the gate to my voltage source, and I'll connect the switch node. Now I'll right click here and go to advanced and select the pulse option. I'll put the initial voltage at 0, so this will be the off state voltage, and the on state voltage will be 15 volts. I'll put the rise and fall times at 100 nanoseconds. So if I keep the rise and fall times too small, it will actually create some problems in the circuit with the reverse recovery of the diode. And if I keep them too large, then it will actually change the duty ratio. So 100 nanoseconds is around 0.5% of my time period, so which is not that bad. For T on and T period, I will use variables. So I'll just write DTS in curly brackets for T on and TS in curly brackets for the period. Now I have to define these values, and I will do that using a SPICE directive. So I will write dot parameter D, which is 0.625, and in the next line write the time period as 20 micro, which corresponds to 50 kilohertz. Then I can run the simulation for 30 milliseconds. So if I probe the output now, I can see at steady state it is around 45 volts. I can see it is actually a bit higher than 45 volts. And if I check the switch node voltage as well, I can actually measure the on time of the switch. So I can see the on time is around 12.6 microseconds. So for a duty of 0.625, the on time should be 12.5 microseconds. And this increase is probably due to the delay time that I had set. And that is why the voltage is actually a bit higher than what we expected. I can also probe the inductor current, and I can measure the ripple in the inductor current. So I can see it is 1.96, which is quite close to 1.898 that I had calculated. Similarly, I can also measure the voltage ripple. Now if I see the switch current, I can see that the switch current is equal to the inductor current during the on time. And there is this initial spike. This is actually due to the reverse recovery of the diode. So if I see the diode current, you can see when the diode turns off, the current goes into a reverse recovery, and complementarily the current in the switch rises. In fact, if I change the diode, if I select a Schottky diode now, I can see here the peak was around 30 amperes. If I run it again using a different diode, I can see that the reverse recovery is very much reduced. LTspice also has the provision for repeating the simulation for different parameter values. So what do I mean by that? I can change this directive and use a step directive instead. So I want my duty to change from 0.4 to 0.6 in steps of 0.1. So I'll write this command, and if I run and I probe the output voltage, I can see that the output voltage changes as the duty also changes. I can see the cursor, and I can switch between the waveforms using the arrow keys. And if I right click on the cursor, I can see that this was for D equal to 0.6. I can do the same for TS as well. I'll undo the command for D, and then instead I'll change the command for TS. This time I'll list the values as 10 micro, 30 micro, and 50 micro. Now it will take some time to run the simulations 3 times. But if I see the output voltage is not very different in this case, if I see the inductor current instead, I can see for 3 different time periods the inductor current ripple increases as the time period increases. So for a given current ripple, I will need a higher value of inductance if my switching frequency is smaller. Now, lastly, I can also check the power at the output. If I undo this step change, and I'll simulate it again. I'll press the Alt key and see the output power. If I zoom in at the steady state region, and if I hold the Control key and press the name of the trace, I can see the average power in this window. And the average power is around 204 or 205 watts. I can do the same for the input. So this time the power is negative again because of the conventions. And if I find the average, it is 206 point something. So there is a small loss, about 1 watt. So this loss is taking place because the switches are not ideal. So there is a small reverse recovery. There must be some switching loss as well as some conduction loss.